Hello, in this video what I'd like to do is go through something called the fundamental theorem of algebra, which really just talks about the number of x-intercepts that a function will have. So your zeros, your roots, your x-intercepts are the x values of that make a function equal to 0. And those can be found on the graph of a function where that graph crosses the x-axis. And here's just some of the notation around it, so we would call those values c, such that our f of that c value is equal to 0. So what I want to do is just go in through a little bit more on the types of these zeros. So a polynomial function, which highest power is n, so that is the degree of the function, has that many zeros, and we call them either real zeros, which can be seen across the x-axis, or complex, and this is going to be our imaginary numbers. So we might not actually see a graph cross the x-axis. Prime example of that would be if I had a quadratic function that was a parabola that looked like this. This function visually does not cross the x-axis. However, if it was a quadratic function and the highest power is 2, we would say that this function has no real solutions, but we would say that it has 2 complex roots. So meaning that, again, we can't visually see real solutions. I can't see this graph cross the x-axis, but the function does have 2 imaginary roots. So the new kind of concept with this as well is that some zeros can be repeated. We call this the multiplicity of something, and we'll kind of get into that in this picture below. And that would really result when a graph touches but not crosses the x-axis. So I've got a graph here to the right, and just to show you that this graph crosses the x-axis visually at -3, at -1, and then it crosses the x-axis at 2 as well. So we would say that this graph, or this equation, has 3 roots that are real roots at -3, -1, and +2, except we would call this a multiplicity of 2, which is a really fancy way of, again, saying that since this root is directly on the x-axis, what would happen is in an equation we would have that factor appear twice. So for example, if I had the factored form of something that said x plus 3, x plus 1, and then I would have x minus 2, I would have one more repeated factor of that x minus 2. And that showed up when we went through quadratics before. If I had a quadratic equation, okay, we're going to pretend that that actually touched. If I had a quadratic equation that crossed the x-axis at one point, we could then make the conclusion that that graph could be something like this, where again I would have that value essentially squared. I have 2 of that value. And then the last thing being these complex roots, and we'll talk about this, how complex roots kind of travel in zeros, or in pairs. So you will have a positive complex root and a negative complex root is some possibilities. So we'll get into some of those types of visuals. First off, just going into a couple examples where we're just going to use some factoring techniques to find all the zeros. So in this first one, I'm going to see that I have a polynomial of 4 terms that is factorable by grouping, meaning I can underline my first 2 and factor something out of here. The greatest common factor for 18 and 27 is 9. I can also factor an x squared out of this, meaning I can divide. I can take 18x to the third divided by 9x squared and get 2x. I can take -27x squared divided by the 9x squared and get -3. Since this is a minus, I'm going to go ahead and bring that down. And then out of these terms, if I do, if I take a 4 out, or if I divide 4 out of each of these, the -8x divided by -4 is going to give me a 2x. And then I have a 12 divided by -4, which is -3. So how grouping then worked is I would take that common factor of 2x minus 3, and then I would also have left over the 9x squared from this side, and then my -4. So this equation is still factorable, actually. We can go a step further, which is to acknowledge that I've got 2 perfect squares here, so I can use my difference of squares formula, which says that the square root of 9x squared is 3x, and the square root of the 4 is a 2. So what I can do is just put a plus here and a minus here. So that was the factored form, and that was what f of x was equal to. So if I wanted then to find my roots, which we want to find the zeros, or our roots of this equation, we're going to take each of the sets of parentheses that I have here and just set them equal to 0 and then solve. So if I do 2x minus 3 equals 0, I can add 3 to both sides and then divide, so I'll get 3/2. For this one, I can do 3x plus 2 equals 0, subtract 2, and then divide, so that one would be at negative 2/3. And then lastly, I would have 3x minus 2 equals 0, so 3x equals 2, and x equals positive 2/3. And with these last two, I want to just kind of go back to, if I did not factor using my difference of squares, I can actually still take this 9x squared minus 4 and set that equal to 0. And I can add 4 to both sides, which would give me this. And if I divided both sides by 9, I would have 4 over 9. And then taking the square root would give me two answers. I would have a positive and negative root, and I would have the square root, I would have the square root of 4 over 9. The square root of 4 is 2, and the square root of 9 is 3. So I would still get my two roots, even if I didn't do that step of factoring. So as far as the graph goes, again, we just found where this graph crossed the x-axis. So if I jump over to the graph of this function, I can see that this root is at negative 0.67, which is negative 2/3. Here's the positive version then of the positive 2/3, and then here's my 1.5, which is my 3/2. So if I go back again, those are all three of my answers. In this second example then, we have another quadratic equation. This time we don't have anything that's factorable. So if I have nothing that I can take out of this, we want to go to our graph and see if there is a real root that I can take out. So here is, I want to leave that. Here's the graph of this function. And what I'm going to do is pick out one of my real roots of this graph, which is really just looking at where this graph crosses the x-axis. And I'm going to pick out this value right here, which is at negative 5. So we know that one of my factors then, so I do have a real root at x equals negative 5. So I'm going to point that out, that we know that x equals negative 5 is one of my answers. What that means is that if I were to factor this equation, x plus 5 would be my factor, and then x equals negative 5 would be the solution. What that allows me to do is use synthetic division with the negative 5 and copy down my coefficients from my polynomial and actually calculate our other roots. So I'm going to bring my 4 down. I have negative 5 times the 4, which is negative 20. Add this going down, I've got the positive 19. When I multiply these two values together, I get negative 95. Add these together, I'll get negative 5. And then lastly, negative 5 times negative 5, which is positive 25. So the fact that I have the remainder of 0 tells me that x plus 5 is one of the factors of this polynomial. So I take the remaining part here and I create an equation out of that. And that equation comes from, again, the fact that we had a cubic function divided by this x. So taking x to the third divided by x means that I'm going to be reducing this to 4x squared plus 19x minus 5. And I'm going to get rid of some of this work from over here before. And what we're going to do then is factor this. So again, realistically, x plus 5 was one of my factors. So I don't want to forget about that. And then I can bring down my f of x equals. And now we need a way to factor this quadratic trinomial. So one of the methods of doing this would be using a star method, which is just one algorithm that says, okay, if I take my a times my c value, put that up there, my b value down there, put my 4 on both sides, and we'll figure out what multiplies to negative 20 that adds up to a positive 19. And that would be a positive 20 and a negative 1. So this 4 over negative 1 is going to give me the factor of 4x minus 1. I have the 4 over the 20, which is really 1 over 5. So then that one's going to turn into x plus 5. And then I've also got this factor from before, which again, I wanted to mention that that is also x plus 5. So my factored, or like my final factored form, it's a lot of f's, final factored form would be to really have 4x minus 1. And then I have this x plus 5 written twice, so it's really x plus 5 squared. So that would be the factored form of our equation. Figuring out where this graph crosses the x-axis, we already knew that this graph crossed at x equals negative 5. So that is one of my solutions. However, that value, or that x equals 5, we would say has a multiplicity of 2, meaning since this x plus 5 was squared, that graph, or that fact right there tells me that my curve is going to be on the x-axis at x equals negative 5. My other 0 would happen if I took 4x minus 1, set it equal to 0, and then solve, and I would get 1/4. So that would be my other answer then. So if I go back to the graph of this, and look, again, this function is a cubic function. So slow down. This function is a cubic function. My degree is 3. My lead coefficient is 4. So my highest power is 4. The odd degree tells me that my arrows, my end behavior arrows, will point in the opposite direction. So this graph goes from bottom left to top right, and we know that I have the potential, that first thing I went through, the fundamental theorem of algebra, tells me that I can have a maximum of 3 zeros of this graph. Well, we can physically see 2 of those zeros. We just know that since this one is on the x-axis, we would say that this value has what we would call a multiplicity of 2. And what I want to kind of get into then is, okay, well, what happens then if we have these imaginary roots? And that's what we're going to take a look at on the next example. And this one is another where, again, I'm going to start from the graph since this is not factorable. If I pull up the graph to this problem, I'm going to pick one of my real roots, which is at negative 3. So I'm going to take x equals negative 3, which tells me that x plus 3 is one of my factors. And we're going to use synthetic division on x equals negative 3. So I have 1x to the 4th, 2x to the 3rd, 22x squared, 50x, and negative 75. And I'm going to bring the 1 down. I know that negative 3 times 1 is negative 3. Add going straight down. Negative 3 times negative 1 is positive 3. That's going to give me 25. I'm going to end up with negative 75 here, negative 25, and then one last time I'll get 75 with my remainder of 0. So this equation that was raised to the 4th power is now going to give me, out of these 4 values, I'm going to have 1x to the 3rd minus 1 of those x squareds plus 25x minus 25, which is now a polynomial of 4 terms. So that tells me, again, I'm going to use the grouping very similar to what I did on one of the first problems that we did, and that is to take out x squared, or divide both first terms by x squared, and that would give me x minus 1. Since this is a positive, I'm going to bring a positive or a plus sign down, and I'm going to factor a 25 out. Be really careful with this. I'm left with x minus 1. So I'm left with x minus 1, and then I've got my x squared and my plus 25. I had this factor before of x minus 3, so I'm going to bring that x plus 3 back down. And this would be my final factored form of the equation. So again, if I take each one of these and set them equal to 0, x minus 1 equals 0, I get x equals 1, tells me my graph crosses the x-axis at x equals 1. We already knew that if I took the x plus 3 and set it equal to 0, I would get that negative 3. So this graph has these 2 real roots, which means that I have 2 other roots. And the reason I know that is because this highest power is 4, tells me I should have 4 answers. The only problem is this is not a difference of perfect squares. If I take x squared plus 25 and I set it equal to 0, if I bring that 25 over to the right-hand side and take a square root of both sides, I'm going to get plus minus the square root of negative 25. Oh boy, square root of a negative. That tells me that we are going to have 2 imaginary solutions. The square root of 25 is 5, and the square root of negative 1 is I. So plus minus 5i would be my other 2 solutions. So if I go back to the graph, I'm going to see this graph cross the x-axis at positive 1, negative 3, and then this plus minus 5i, which again, we cannot actually see. So here's my negative 3, and here's my positive 1. So the graph, again, has 4 roots, but 2 are real, and then 2 are imaginary. Okay, if we had 3 places that this graph crossed the x-axis, that means that, again, I would have to have some curve that looked like this, where I could have a multiplicity of 2. So if I saw a graph physically only cross the x-axis 3 times, but its power was 4, I would need to have a multiplicity at one of my other zeros. It would be impossible for me to have a function that is raised to the 4th power and have 3 real and 1 imaginary, or 1 real and 3 imaginary roots. The imaginaries travel in pairs. And that's really the last one that I want to go through then, is when I have a problem that is a cubic function. I have a cubic function where we're going to end up with, again, seeing that the imaginary roots are going to travel in pairs. So on this last example, I can factor by grouping right away. And if I factor by grouping, okay, if I factor this by grouping, I can take out, so I can say f of x equals, and I can take out an x squared, and I'm left with x minus 5. And then out of these two terms, I can take out a 16, and I'd be left with x minus 5. So this is going to simplify into x minus 5, and then I have x squared plus 16. And very similar to the last one. So this would be my factored form. So this is a lot shorter of a problem. This is my factored form. Again, I cannot break this up into x plus 4 and x minus 4 because of the plus sign in the middle. So what I'm going to do is take each of my factors, which is what these two things are, and set them equal to 0. I get x equals positive 5. That is my one real solution, which again, go back to your highest power. My highest power is 3. So if I have 3 solutions, I can either have 3 real and no imaginary, or my 1 real, and then in this case, I'm going to end up with 2 imaginary solutions. And that is because when I take that square root, I'm going to put a plus minus the square root of negative 16. I'm going to take the square root of 16, which is 4, and then the square root of negative 1, which is I, and then I'm going to have my other 2 answers. So I have 1 real and 2 imaginary, or sometimes you'll see them called complex solutions. And if I go to the graph of this, here's my real solution at 5, 0, which again, that's what we expected, was for our 1 solution to be at 5, 0. And then I cannot see my 2 imaginary solutions because they are imaginary.